For years, the race to build better AI chips has been measured almost entirely by one metric: performance. Every new generation promises more computing power, more transistors, and faster processing speeds. The assumption has been simple: the company that builds the fastest chip will lead the future of artificial intelligence. But that view overlooks a growing problem that every major chipmaker is now confronting. As AI models become larger and data centers become more powerful, the greatest challenge is no longer just generating more computing power. It's removing the enormous amount of heat that computing creates. Every increase in performance also increases thermal stress, forcing engineers to rethink how the next generation of AI hardware is designed. In many cases, performance is no longer limited by processing capability, but by how efficiently that heat can escape. Surprisingly, one of the most promising solutions isn't a revolutionary new processor architecture. It's a material that has been valued for centuries for entirely different reasons: synthetic diamond. Once associated almost exclusively with jewelry and industrial cutting tools, lab-grown diamond is now attracting serious attention from the semiconductor industry because of one remarkable property: its ability to conduct heat more effectively than almost any other known material. That shift raises a fascinating question. If thermal management becomes the defining constraint of advanced AI hardware, could the companies and countries leading in advanced materials gain an advantage just as important as those designing the chips themselves? That's the story we're exploring today. Behind every AI chatbot, image generator, recommendation engine, and autonomous system lies a vast network of data centers operating around the clock. These facilities contain thousands of specialized processors, performing trillions of calculations every second. While the public often focuses on the intelligence of the software, engineers are increasingly focused on something much more fundamental: keeping the hardware cool enough to continue operating. Modern AI processors consume extraordinary amounts of power. Unlike traditional CPUs, today's AI accelerators are designed to handle enormous workloads continuously, often running at maximum capacity for extended periods. Nearly every watt of electricity consumed by these chips eventually becomes heat, and that heat must be removed quickly to maintain stable performance. Cooling systems have become one of the largest operating costs inside advanced data centers. Air cooling, once sufficient for earlier generations of hardware, is gradually giving way to liquid cooling and increasingly sophisticated thermal management systems. In many facilities, a significant portion of total electricity consumption is dedicated not to computation itself, but to preventing processors from overheating. As semiconductor manufacturers continue packing more transistors into smaller areas, computing density rises dramatically. More computing power delivered from the same physical space inevitably produces greater heat concentration. Even modest increases in chip temperature can reduce efficiency, shorten component lifespan, and limit how aggressively processors can operate. Engineers refer to this as a thermal bottleneck. A processor may be capable of delivering higher performance, but if heat cannot escape quickly enough, the chip must automatically reduce its operating speed to protect itself from damage. In other words, the limitation isn't always the computing architecture, it's the ability to remove heat fast enough. This is why thermal engineering has become one of the semiconductor industry's highest priorities. Every improvement in cooling allows chips to sustain higher performance, consume energy more efficiently, and operate more reliably over longer periods. As artificial intelligence continues expanding across cloud computing, scientific research, and enterprise applications, solving the heat problem is becoming just as important as designing faster processors. And that has led researchers to revisit a material whose thermal properties have been understood for decades, but whose practical use in semiconductor manufacturing is only now becoming realistic. When most people hear the word diamond, they think of jewelry, luxury goods, or gemstones locked away in display cases. Engineers, however, see something entirely different. To them, diamond is one of the most extraordinary materials ever discovered, not because of its appearance, but because of the way it handles heat. Every material transfers heat at a different rate. Some hold on to it, causing temperatures to build rapidly. Others move it away efficiently, allowing equipment to remain cool under heavy workloads. In advanced computing, this property has become increasingly valuable as processors continue pushing the limits of performance. For decades, silicon has been the foundation of the semiconductor industry. It is exceptionally well suited for building transistors, which is why nearly every modern processor relies on it. But silicon was never selected because it was the best material for thermal management. In fact, compared with several other materials, its ability to conduct heat is relatively modest. Copper performs considerably better and has long been used in heat sinks, cooling plates, and thermal interfaces throughout the electronics industry. Yet even copper has limits. As AI accelerators become more powerful and transistor density continues increasing, traditional cooling materials are approaching the point where further improvements become increasingly difficult. This is where diamond begins to stand apart. Among naturally occurring materials, diamond possesses one of the highest thermal conductivities ever measured. Heat travels through it remarkably quickly, allowing thermal energy to spread away from hotspots before temperatures reach damaging levels. For semiconductor engineers, this makes diamond an exceptionally attractive candidate for advanced thermal management. Importantly, the industry is not looking at diamonds as decorative objects or even as gemstones. The material used in semiconductor applications bears little resemblance to the polished diamonds found in jewelry stores. Instead, manufacturers produce extremely thin synthetic diamond films engineered specifically for industrial use. These materials are designed to meet demanding technical standards rather than aesthetic ones. For many years, however, there was one major obstacle. Scientists understood diamonds' thermal advantages long before artificial intelligence became a global priority. Research papers describing its remarkable physical properties have existed for decades. If the material offered such obvious benefits, why didn't the semiconductor industry adopt it much earlier? The answer wasn't a lack of understanding, it was manufacturing. Producing laboratory-grown diamonds suitable for electronics proved extraordinarily difficult. Semiconductor applications require materials with exceptional purity, microscopic uniformity, and surfaces polished to almost atomic precision. Even tiny imperfections can interfere with packaging processes or reduce thermal performance. Growing diamonds was one challenge. Producing them consistently, economically, and at industrial scale was another entirely. As a result, diamond remained largely confined to specialized scientific equipment and niche industrial applications. The technology simply wasn't mature enough to support widespread semiconductor manufacturing. That situation, however, has begun to change. Advances in synthetic diamond production have dramatically improved both quality and scalability, transforming a material once considered impractical into one that major semiconductor companies are now evaluating for next-generation AI hardware, and that manufacturing breakthrough may prove to be every bit as important as the material itself. The remarkable thermal properties of diamond have never been a mystery. Materials scientists have studied them for decades, and semiconductor engineers have long recognized the material's potential. The real challenge was never discovering what diamond could do. It was finding a way to manufacture it consistently, economically, and at the scale required by the global chip industry. Producing synthetic diamond is far more complicated than simply growing crystals inside a laboratory. Semiconductor applications demand extremely thin films with exceptional purity, almost perfectly smooth surfaces, and microscopic consistency across every layer. Even the smallest structural defect can reduce thermal performance or prevent the material from integrating properly with advanced chip packaging. These requirements placed diamond beyond the reach of commercial semiconductor production. Manufacturing costs were high, production volumes were limited, and achieving consistent quality proved extremely difficult. As a result, most chipmakers continued relying on conventional cooling materials, even though they understood those materials were approaching their physical limits. Over the past few years, however, the situation has changed dramatically. Advances in chemical vapor deposition and precision manufacturing have significantly improved the ability to produce synthetic diamond films suitable for electronics. Researchers have refined techniques that allow diamonds to be grown with greater uniformity, fewer impurities, and surface finishes compatible with advanced semiconductor packaging. Just as importantly, these improvements have begun moving production from laboratory-scale demonstrations toward industrial manufacturing. That transition represents a major milestone. Throughout the semiconductor industry, many breakthrough materials remain confined to research papers because they cannot be produced economically in large quantities. A material only becomes commercially valuable once manufacturers can deliver consistent quality, predictable yields, and competitive costs. In many ways, manufacturing capability is just as important as scientific discovery itself. As production methods improved, interest from the semiconductor industry accelerated. Companies developing next-generation AI processors began evaluating synthetic diamond not as an experimental material, but as a practical solution to one of their most pressing engineering challenges. Instead of asking whether diamond could improve thermal performance, attention shifted toward questions of integration, supply capacity, long-term reliability, and compatibility with existing packaging technologies. That shift signals an important change in perspective. The conversation is no longer centered on whether synthetic diamond works in theory. Engineers now understand its thermal advantages. The discussion has moved toward how quickly it can be incorporated into commercial semiconductor manufacturing and how broadly it can be deployed across future AI hardware. This growing interest has also drawn attention to the countries and companies capable of producing the material at scale. Among them, China occupies a particularly significant position. Over many years, Chinese manufacturers built extensive expertise in synthetic diamond production for industrial applications, creating manufacturing capabilities that now appear increasingly relevant to the semiconductor industry. In other words, the scientific breakthrough was only one part of the story. The equally important development was that an industrial supply chain was already in place, ready to support a technology that the AI industry suddenly needed. And that brings us to the next question. How exactly does diamond fit inside an AI chip? And why can a thin layer of this material make such a meaningful difference to performance and efficiency? One of the biggest misconceptions about synthetic diamond is that it will replace silicon as the foundation of computer processors. That isn't what semiconductor engineers are trying to achieve. Silicon remains exceptionally well suited for building transistors, and there is no immediate indication that it will lose that role. Instead, diamond is being explored for a different purpose, helping those silicon chips operate more efficiently by improving how they manage heat. To understand why this matters, it helps to picture what happens inside an AI processor during operation. Billions of transistors switch on and off every second, performing calculations at incredible speed. Every one of those operations generates a small amount of heat. Individually, the effect is tiny. Collectively, across billions of transistors working simultaneously, the result is an intense concentration of thermal energy in a remarkably small area. It must travel through multiple layers of packaging before eventually reaching a cooling system. Each layer acts like a roadway carrying traffic away from a busy city. If any section of that route becomes congested, heat begins to accumulate near the processor itself, raising temperatures and reducing performance. This is where advanced packaging has become just as important as chip design. Modern semiconductor packages are no longer simple protective shells. They have evolved into highly engineered systems responsible for electrical connections, structural support, signal integrity, and increasingly, thermal management. Engineers are constantly searching for materials that can move heat away from sensitive components more quickly and more efficiently. Synthetic diamond offers an unusually attractive solution. Rather than replacing the processor, extremely thin layers of diamond can be integrated into the package beneath or around the chip, creating a highly efficient pathway for heat to travel toward cooling systems. Because diamond conducts heat so effectively, thermal energy spreads more rapidly instead of remaining concentrated around the processor. The practical benefits can be significant. Lower operating temperatures allow processors to maintain higher performance for longer periods without automatically reducing clock speeds. Stable temperatures also improve long-term reliability by reducing thermal stress on delicate semiconductor components. Over time, that can extend hardware lifespan while lowering maintenance and replacement costs for operators of large AI infrastructure. The impact becomes even more meaningful at the scale of modern data centers. A single AI cluster may contain thousands or even tens of thousands of accelerators operating continuously. Even modest improvements in cooling efficiency at the individual chip level can translate into substantial reductions in electricity consumption across an entire facility. Lower cooling requirements also make it easier to increase computing density, allowing more processors to operate within the same physical space without exceeding thermal limits. Better thermal materials enable higher sustained performance. Higher sustained performance improves the productivity of expensive AI hardware. More efficient hardware reduces cooling costs, which lowers operating expenses for cloud providers and enterprise data centers. Those savings can then be reinvested into additional computing capacity, accelerating the deployment of increasingly advanced AI systems. Perhaps most importantly, improved thermal management gives chip designers greater flexibility for future generations of processors. As transistor counts continue rising and AI models demand ever more computing power, engineering breakthroughs will depend not only on making processors faster, but also on ensuring they can operate safely under increasingly demanding conditions. Materials that remove heat more effectively may become just as valuable as innovations inside the silicon itself. When people think about semiconductor leadership, they usually picture chip designers, fabrication plants, or advanced lithography machines. Far less attention is given to the industries that supply the materials making those chips possible. Yet history has shown that manufacturing expertise often becomes a strategic advantage, long before the broader market recognizes its value. Synthetic diamond may be the latest example of that pattern. Today, however, those same manufacturing capabilities are attracting attention from the semiconductor industry. Producing synthetic diamond for electronics demands exceptionally high standards, but many of the underlying production technologies already exist within an industrial ecosystem that has spent years improving quality, consistency, and manufacturing efficiency. That gives China an important starting point. Instead of creating an entirely new industry from the ground up, manufacturers can adapt existing expertise toward higher value semiconductor applications. The transition is certainly not automatic. Electronics-grade materials require much tighter specifications than industrial products, but the knowledge, equipment, and production infrastructure already provide a meaningful foundation. This illustrates an often overlooked reality of advanced manufacturing. Competitive advantages rarely appear overnight. They are usually the result of long-term investments made for reasons that may have had little connection to future technologies. A country may develop expertise serving one industry, only to discover years later that the same capabilities become valuable in an entirely different market. The semiconductor industry has experienced this kind of transition before. Manufacturing processes originally developed for consumer electronics eventually supported advanced displays. Precision materials, created for aerospace, later found applications in high-performance computing. Skills acquired through decades of industrial production often become unexpectedly important as technology evolves. As semiconductor companies evaluate new thermal management solutions, supply chain reliability becomes just as important as laboratory performance. Chip manufacturers need partners capable of producing large volumes of material with consistent quality, predictable delivery schedules, and continuous process improvements. Those requirements favor regions that already possess mature manufacturing ecosystems rather than experimental production facilities. This is one reason industry observers are paying close attention to China's position. The discussion is no longer simply about who discovered a promising material. It is increasingly about who can manufacture that material at commercial scale while meeting the demanding standards of advanced semiconductor production. Scientific breakthroughs may begin inside research laboratories, but widespread adoption depends on factories capable of delivering reliable products year after year. At the same time, it is important to keep the broader picture in perspective. Semiconductor supply chains remain highly international. Companies across North America, Europe, Japan, South Korea, Taiwan, and China continue contributing critical technologies, equipment, and manufacturing expertise. No single country controls every stage of advanced chip production. However, leadership in one strategic component can still create meaningful influence. If synthetic diamond becomes an increasingly important part of next-generation AI chip packaging, manufacturers with established production capacity could find themselves occupying a far more significant position within the global semiconductor supply chain than they did only a few years ago. And that leads to an even bigger shift in perspective. The future of semiconductor competition may no longer be decided solely by who designs the fastest processor. It may increasingly depend on who controls the advanced materials, packaging technologies, and manufacturing ecosystems that allow those processors to perform at their highest potential. For decades, the semiconductor industry measured success primarily by one standard: who could design the most advanced processor. Faster transistors, smaller manufacturing nodes, and greater computing power defined technological leadership. Those factors remain critically important today, but they are no longer the entire story. As AI models become larger and data centers consume unprecedented amounts of electricity, the industry's biggest engineering challenges are expanding beyond the processor itself. Performance now depends on an entire ecosystem of supporting technologies, including advanced packaging, high-speed memory, interconnects, cooling systems, and increasingly the materials that allow all of those components to function together efficiently. In many respects, the AI chip is becoming only one piece of a much larger engineering puzzle. Today's competition extends from chip architecture to advanced manufacturing techniques, specialized materials, power delivery systems, and sophisticated packaging technologies. Each innovation may appear incremental on its own, but together, they determine how efficiently AI infrastructure performs at scale. The implications reach well beyond technology companies. Governments increasingly recognize semiconductor supply chains as strategic assets, while cloud providers are investing billions of dollars in AI infrastructure that must remain competitive for years after installation. Every improvement in energy efficiency, cooling performance, or manufacturing capability can influence operating costs across facilities containing tens of thousands of processors. That changes how competitive advantage is created. Instead of relying on a single breakthrough, future leadership is likely to depend on coordinating multiple areas of expertise simultaneously. Chip designers, material scientists, manufacturing specialists, equipment suppliers, and packaging engineers all become essential contributors to the final product. Success is increasingly determined by the strength of the ecosystem rather than by any individual component. This broader perspective also explains why seemingly unrelated industries are beginning to intersect with artificial intelligence. Materials originally developed for industrial manufacturing are finding applications in semiconductor packaging. Advances in precision engineering are influencing data center design. Research that once appeared highly specialized is now becoming commercially significant because AI hardware demands continue rising. The result is a semiconductor industry that looks very different from the one that existed only a decade ago. The next major breakthroughs may not come solely from designing smaller transistors. They may emerge from combining innovations across materials, science, manufacturing, packaging, and thermal engineering into systems capable of supporting the extraordinary computing demands of future AI. And if that trend continues, the race for AI leadership will increasingly be decided not just by who builds the fastest chip, but by who assembles the most complete and resilient technology ecosystem around it.